In the last lecture, we discussed the force between charges. This force is given by Coulomb's law. That is, the force between two charges placed at a distance r is 1 by 4 pi epsilon 0 q1 q2 by r squared. That is the magnitude of the force. We also saw the expression for the force in a vector form. Then we defined the field of a charge and found the expression for the field of a charge q. Now, we shall introduce the concept of lines of force. Lines of force is a very important concept. This is common to all fields that you study in physics. The electrostatic fields, the magnetic field, the gravitational field, all these fields are defined in terms of lines of force. So, let us take the electric lines of force. Things would be similar in magnetic lines of force and gravitational lines of force. A convenient and pictorial representation of an electric field is through the lines of force or field lines. The field lines are only imaginary lines. Now, this is important to remember. There are no lines. If one charge is here, another charge is here, there are no lines. These are only imaginary lines. These lines are drawn to map the electric field. So, what are the properties of these lines of force? First, an electric field line is such that a tangent to it at any point gives the direction of the field at that point. That is, if this is the line of force, the tangent at the point P is in this direction, and therefore, this gives the direction of the field at point P. A field line starts at a positive charge and ends at a negative charge, and if there are no opposite charges present, the lines of force due to a positive charge must extend to infinity, and due to a negative charge, they must appear to come from infinity. If there are two kinds of charges, then the lines start at the positive charge and the end at the negative charge. You see, the lines are ending at the negative charge. Here the lines are moving out of the positive charge. Field lines are always perpendicular to the surface of a conductor, because if they were not, they would have a component along the surface of the conductor. You see, we have defined lines of force as such that the tangent to them at any point is the direction of the line, is the direction of the field. So, if a line is at an angle to this, say in this angle, this is the line of force, then what happens? It will have a component along the direction of this conductor, and that means this field will then move the charges, because this will exert force on charges and they would move. Since the charges are static, obviously there cannot be any component like this, and therefore, the lines of force must be perpendicular at each point to a surface on which the charges are distributed uniformly, that is, the surface on which the potential is constant. Since there cannot be any field along an equipotential surface, lines of force must be normal to it, as we saw here. This is a uniform charge distribution or charge distribution, the potential is constant, therefore, this is a equipotential surface and the lines of force are perpendicular to this. The relative density of lines of force indicates the strength of the field. If in a region you have lines of force, say same region, but the number of lines of force here is larger than the number here, then this field is stronger than this field. The straight and equally paced lines indicate a uniform field. These lines are straight, they are equally placed, therefore, this represents a uniform field. Whereas, these lines, although they are uniformly placed, but they are curved, they are not straight, therefore, they represent a non-uniform field. Two field lines cannot cross. You see, if two field lines are like this, one like this, one like this, one like this, then there will be two tangents at the point O, and that means there will be two directions of the field at point O. But from the principle of superposition, we know that the field direction at a given point must be unique. There cannot be two directions, and therefore, the two lines of force cannot cross each other. An important property of the lines of force is that there is tension along their length, that is just like the stretched springs, and as soon as I give them up, as soon as I leave the spring collapses, it comes back to the original position. So, these lines of force have tension along them, and therefore, they tend to shorten their length, and in an attempt to shorten their length they produce attraction between opposite charges. There are also lateral pressure. If these are lines of force, then this is called lateral direction. So, there is a lateral pressure, they tend to press perpendicular to their direction. If the lines are like this, then they press in this direction. And what happens because of this? Say these are lines due to two positive charges and these are lines due to two negative charges. What happens? The lines at this point here, they are going like this or they are coming like this, they repel each other. There is a pressure in the sideways direction, and therefore, they produce repulsion in the charges. When there are two positive charges or whether there are two negative charges, these lines of force because of lateral pressure produce repulsion in the charges. Now, if we have two plates as we have in a capacitor, one positively charged, the other negatively charged, then the lines of force are from positive to the negative, away from the edges. Towards the edges they are slightly bent, but away from the edges these are the lines of force. To consolidate the concept of lines of force, we will take this very simple example, but very illustrative example at the same time. We have a isolated conducting sphere uncharged, and we bring a charge, say in this case negative charge. What happens? This negative charge will induce a positive charge here and a negative charge there, and the lines of force must end at the negative charge. Therefore, the lines of force will be like this, and they must proceed from the positive charge. Therefore, they will be like this, and here the lines of force must be coming to the negative charge. If there is a positive charge, then it produces a negative charge on the near side and a positive charge on the far side, and the lines of force must emanate, must go away from the positive charge. So, they are going away, and here is the negative charge, here is a positive charge. Therefore, the lines of force go from positive to the negative charge, and positive charge, the lines are going away from the positive charge. So, this tells you what the properties. In fact, this sums up the properties of lines of force. Let us take another example. As an application of the Coulomb's law and the use of symmetry of the system, let us find the electric field at the center of a semicircular wire of radius a, having charge lambda per unit length. Let me show you the diagram first. We have a semicircular wire which is uniformly charged. Per unit length it has charge lambda. So, we are required to find the field at this point, at the center P of this semicircular wire. So, what happens? If there is a positive charge, then there is a charge on length dl, which is lambda times dl, and this produces a field in this direction, the field away from the positive charge in this direction, and a corresponding element here at m will produce a field in this direction. So, we can take the components of these fields and we will see that this component along this direction, this component of this along this direction will be this, the component of this along this direction will be this. So, they will cancel. All that we have is the component in this direction, that is component of this in this direction. So, we can calculate, you see, in this direction. So, calculation is easy. The intensity of the field is lambda. You see, let me explain the geometry again. What is dl? dl can be expressed in terms of angle theta. It is a d theta, dl is a d theta. So, one can express that. So, dE is 1 by 4 pi epsilon 0 lambda times dl, which is lambda a d theta by a squared into sin theta, because there is a sin theta component that is available to us. The cos theta component vanishes. So, sin theta, and the field at P due to the whole wire, then theta varies from 0 to pi, and therefore, E is 1 by 4 pi epsilon 0 lambda by a I can take out, and then integral of sin theta d theta, which gives 1 by 4 pi epsilon 0 2 lambda by a. The direction of the field is along P x if this charge is positive. If this charge is negative, the direction would be the opposite. If I complete the circular wire, what will happen? Due to this half, the field would be in this direction. Due to this half, the field would be in this direction, and the two will cancel. So, at the center of a circular wire, we do not expect any field. we shall verify this by using Gauss theorem later on. Now, let us take variation of the same thing. We have a positive charge on this quarter and a negative charge on this quarter. Now, what happens? The positive charge here produces a field in this direction, of which the components are this and this. The negative charge in the corresponding element produces a field in this direction, which has a component along this and along this. Now, these two components along P x and P r, they will cancel, and only this component will be available to us. This will be non-zero, these two will cancel each other, and now we can calculate what the field would be at the point P. The direction of the field at point P is P y. If this is positive, this is negative. If this is positive, this is negative, then it will be the direction P z. So, we can calculate. We know that these two components are being added. So, and we can express the components in terms of angle theta. So, the field E along P y is 2, because this is due to both the elements here on this side and on this side, positive and negative. Therefore, it is 2 into 1 by 4 pi epsilon 0 lambda by a into 0 to pi by 2. Now, theta varies from 0 to pi by 2 cosine theta d theta, because cosine theta is the component that does not vanish. So, we can calculate and gives us this, because each half has theta going from 0 to pi by 2. So, the intensity is, the magnitude of the intensity is 1 by 4 pi epsilon 0 2 lambda by a. So, let us take another example. We have a charge q which is split into two parts, one is q, the other is q minus q, and we find force between them, and we want to maximize this force. So, we will take df by dq and put that equal to 0. From this we shall find that q must be equal to q by 2, that is, the charge must be split into two equal parts, so that the force between them is maximum. Now, every field is defined in terms of a potential. So, whenever there is a field, we can define a potential, and the definition is this: E is equal to minus grad phi, where grad is a quantity given by this I d delta by delta x plus j delta by delta y plus k delta by delta z. However, if there is spherical symmetry, that nothing changes if you rotate something around theta or around phi, there is a spherical symmetry that however you rotate, you see the same thing, that is called spherical symmetry. If there is a spherical symmetry, then that gradient becomes r cap into d by dr, just simple d by dr. So, therefore, the electric field in a spherical system is given by minus d phi by dr r cap. This minus sign we shall take care of in a moment, I shall explain, but it is given by minus d phi by dr r cap. If the field is only along the x direction, then E is equal to minus d phi by dx. Now, we have seen the electric field due to a charge in the last lecture is 1 by 4 pi epsilon 0 q by r squared r cap, and from this we can guess what phi would be, and phi turns out to be this. We can verify this, and we show that if I take d phi by dr, then we get this expression. So, that is why this negative sign was there, so that the field given by this, by the potential, has the same sign as the field itself. So, that is why minus sign was introduced for consistency, that the field given by this would be the same as this. So, knowing one of the quantities E or phi, we can find the other, and the units of electric field in terms of potential is volt per meter, because you know it is volt per meter. Now, suppose we have a positive charge here, what happens to the potential? The potential is 1 by r, potential is 1 by r, and therefore, the potential as r increases, the potential decreases. So, from the positive charge, the potential decreases. We also know that if I place a positive charge here, it will be repelled and therefore move in this direction. So, therefore, a positive charge moves from a higher potential to a lower potential. A negative charge, on the other hand, moves from a lower potential to a higher potential. Here again, we also know that a positive charge, if I place here, it will move in this direction, and this is the direction of negative, this is the direction of decreasing potential. Therefore, a positive charge moves in the direction of decreasing potential, a negative charge moves in the direction of increasing potential. So, here I show you this is a charge plus q here is the potential is like this, decreasing towards infinity as r goes to infinity. So, as 1 by r. Now, a positive charge moves from higher potential to a lower potential, and a negative charge, red arrow, moves from a lower potential to a higher potential. That is, if I place a negative charge near a charge, it moves like this. If I have a positive charge here and I place a positive charge here, that moves like this towards the lower potential, and a negative charge moves towards the higher potential. Here I show the potential due to negative charge. The potential is again 1 by r, but minus 1 by r this time. So, here it is at q equal to 0, it is minus infinity, and then it goes to infinity at r goes increases. So, the shape is like this, and the positive charge moves from infinity towards the negative charge, and towards from a higher to a lower potential. A negative charge, red arrow, moves from a lower potential to a higher potential. The two move in opposite direction. Positive charge moves from a higher to a lower potential, and negative charge moves from a lower to a higher potential. So, in this lecture we have learned two things. One, lines of force, we have also seen their properties, and we have learned about the potential, which is given by, if E is in the x direction, then it is minus d E, the electric field is minus d phi by dx. So, therefore, the unit of electric field is phi by x, that is volt per meter. In the next lecture, we shall take up the electric dipole, and we shall see how it behaves in an electric field and so on.